Hello, welcome to the Physics 171 Case Study Labs. Some of you have taken Physics 170 and may recognize my digitized face here. For those of you who didn't take 170, welcome. This is going to be a ride. So, what are the case study labs? What are we doing here? As with 170, we are continuing this trend of, I'm assuming I don't need to make you better at homework. So we're going to go beyond that and do something interesting. And what we are going to do is we're going to have 3 case studies about not a specific thing like a homework problem, but about a general topic that we're going to look at from a couple different angles. I know that sounds real nebulous, so allow me to explain. What is the big goal of case study? Well, the big thing here is that when you're studying physics, a lot of the times things seem like many isolated data points. You learn Ohm's law, you learn Coulomb's law, you learn Newton's second law, you learn frictional forces, and it's all these like little bitty pieces. In reality, there are some very big overarching things that are underlying everything, if I can mix a metaphor. And the idea of case study is that we are going to look at those. And to really see those kind of big arches, we're going to look at them from a couple different angles. So hopefully you'll be able to triangulate in on this kind of theme. So there are going to be 3 big case studies that we're looking at. There is going to be intensity at a distance, where we're looking at various phenomenons that can all be summarized as something is radiating out energy of some kind, or it produces some intensity field, and how does that change as a function of where you are? That's going to be cycle 1. Cycle 2 is going to be resistance phenomenon. There are many things that can be explained either as an object moving through a fluid or a fluid moving down an object. And that can be used to explain a whole bunch of different physics. So that's studying that one. And then the third one is going to be exponential behaviors. We're going to look at a few things that are all exponential, and why are they all exponential, even though they're coming from all different places. So those are the 3 big arcs, and the way we're going to study each arc is by looking at 5 experiments. Now, some of you are probably pretty fast on the math. You're going, oh no, I have to do 15 experiments this semester. No, you are going to do 3 experiments this semester. Your group is going to do 3 experiments. And then the other 4 groups in your section are each going to do a different set of 3 experiments. So you're each going to do 1 intensity experiment, and then 1 resistance experiment, and then 1 exponential experiment. But you're going to learn and understand and absorb and conceptualize and make it a part of your very being 15 experiments. Because you are going to be learning from everyone else. So, what is that going to look like in a day-to-day nuts and bolts kind of fashion? Each cycle is going to stretch across 4 Wednesdays, which sounds like a lot. I promise it isn't. And it's going to form a schedule that looks like this. So week 1, going from Wednesday A to Wednesday B, is when you're going to be doing most of your work. There's going to be an introductory video, like this one, about what is the cycle, what are the experiments, what do we care about, that kind of stuff. Then your group is going to get a lab procedure and a set of data that has been collected for that experiment. You are then going to analyze that data, crunch all those numbers, come to that conclusion, and write up your report about that experiment. That report is going to be a presentation. So you're going to record a 10-minute presentation Those of you who have been in 170, you have a good idea of what I have in mind when I say that. Don't worry, we're going to talk about it more when we get there. You're going to do a presentation about your experiment, the background necessary to understand it, what was going on, how it fits into the things. That presentation is going to be turned into me by Wednesday B. From Wednesday B to C, I'm doing all the work. I'm going to grade all of the reports. I'm going to analyze all of the presentations, my analysis, kind of crunching the things together. Then I'm going to annotate all of them with my notes, what was good, what was bad, what was missing, all of that kind of stuff. And then I'm going to post all of the videos up publicly meaning within us, with all of my notes, so that that is now available for you. Then we get to week C to D. Now it's your turn to do work again. You as an individual are going to watch the presentations for all the groups in your section that you weren't in. So you're going to learn about those experiments. You're then going to write a report summarizing those experiments and kind of figuring out what the connective tissue is here. How is each one like your experiment? How is it different than your experiment? How do all of these things intersect into the arc? What is the big picture of that cycle that is created by these 5 experiments? Then we take a week off where I'm going to do grading and stuff, and that's going to bring us back to another Wednesday A when we're going to start the next experiment. One question that I hear some of you already rhetorically asking on the other side of your computer is, what are these groups? How's that going to work? That is going to be up to you folk, and I trust that this is going to happen civilly. On Canvas, there are groups 1 through 5 for each of the lab sections. I'm going to leave it up to you to self-select yourself into those groups in your section. So make sure you're not stealing someone else's group, right? Jumping into other people's sections, that kind of thing. And I'm going to let you do all of that negotiating politics to figure out those groups. But once we have those groups, that's going to be your group. And then based on which group you chose, 1 through 5, or you were assigned or harangued into, we'll see. Based on which of those is going to determine which experiments you then do for the rest of your semester. That's going to pick your first experiment, and then based on your first experiment, you're going to get assigned your second experiment, and so forth. So figuring out those lab groups, that's how you're going to figure out who you're going to be working with and what experiments you're going to be doing. So I think that is most of the big picture of physics case study that I want to tell you about right now. As we start the first cycle, there will be more things, but right now we are in week 0, and we have some kind of baseline, getting yourself established things that we're going to cover. The first one, if you haven't already, you might want to download Logger Pro, get used to Canvas, all that kind of infrastructure stuff to get yourself ready to go into this. There is also an assignment this week about experimental analysis, which is how to do some of the tools that you're going to need to talk about this. So we have some slides kind of setting you up for that. And then there's going to be an assignment. So let's not waste any more time. Let's jump into those slides. Experimental analysis. That's kind of a generalized way to talk about how to do experiments well. Those of you who have had me before, a lot of this is going to look real familiar, so I'm going to run through it. So hopefully, if you don't know what I'm talking about, you'll catch on. So, first, uncertainty in measurements, error, all of that. We got to talk about that again? Yeah, we got to talk about that again. So, every measurement has uncertainty. Every procedure has error. What is uncertainty? Uncertainty is how much you trust your results. Error is how much do the results you get resemble the results you were expecting. That is not to say were they wrong, that is, do they match expectation? There are a lot of sources of error. There are a lot of things that can produce error. There are a lot of things that can produce uncertainty. The big one that I'm going to harp on you, you've heard me say this before, most of you, there's systematic error, things that you could engineer away. There's random error, fluctuations in the universe that will cause things to always happen a little bit differently. And then there's the euphemism, human error, which is an admission of guilt that you messed up the measurements and you couldn't be bothered to fix it. Human error is an admission of guilt. Error and uncertainty can propagate. If you have some unknown and it interacts with another unknown, it's going to expand outwards somehow, like these rules are. I don't expect you to memorize them. You shouldn't be writing these down. They're things you can look up. What's important is that you know there is a system to handle this. Here's a much more important one, right? Propagation is more like, how do your error bars look at the end of this? What's more interesting is, how do you combine a bunch of variables into one thing? So let's take a look at this equation here, right? This is vaguely something with pressure. You don't need to know what. The point here is that L is a variable, and R is a variable, and P is a variable in this equation. 3 variables. How do you graph 3 variables? Well, the simple way to do it is to make 3 graphs, but that's really not helpful. A much more interesting way to do it, a much more illuminating way to do it, is to combine variables. So in this example here, we can take R and L and combine them together to make a single variable effectively. And we can graph things on the R to the 4th over L axis, which then allows us to take all of this data and make it into one graph. One graph that tells you how everything is behaving. While we're talking about graphing, a very important thing, a very powerful thing, probably the reason we graph more than anything, is fitting graphs. So let's take a look at this equation here, right? We have that the intensity should be proportional to 1 over r squared. It's a point source. Hopefully you've seen that by now. But this equation makes some fundamental assumptions about what we're seeing. Some of this are things like all of our measurements are exact. There are other things here, like at infinity it goes to 0. What if it doesn't go to 0? What if there's a background level that it never goes beneath? What about the fact that at 0, this says it should go to infinite intensity, which is almost always a hard thing to measure and can cause a real problem. So how do we deal with these things? How can we make a fit that is robust enough to handle all of this real world kind of things? Well, we do that by making a fit that looks like this. So you can see here we have almost the same fit, except now we've thrown a few more knobs that we can turn to really dial this in. So as before, we have that fitting A up on top, but now we have this B, right? R plus B. In this case, B is any uncertainty in R can go in there. If we accidentally started measuring at 1 meter instead of 0 meters, or what if the sensor is actually a couple centimeters into your device, but you don't know how far into the device? Well, in this case, if you throw that B in there, your fit can now tell you how far into the device your sensor is, because it can fit your data and go, you know, this would look a lot better if your sensor was actually at -2 centimeters. And the fit can now tell you that. There's also that C at the end there. The C at the end is your background. At r equals infinity, If there's still some intensity floating around, that's that C, like a background noise, a background radiation, a background light intensity, something. So you have that C that can now handle that. We now have these empirical measurements that can fill in. That fit still made a big assumption though, that it was R squared. What if we don't know if it's squared? Can we let a fit choose an exponent? Well, if we just let a fit choose an exponent, that's going to be bad. That's going to be almost always terrible. And if you don't believe me about why the computer would be bad about fitting an exponent, here you go. In your brain right now, picture an x squared, right? That parabola. Yeah. Now picture an x to the 4th, an x to the 6th, an x to the 8th. Can you tell the difference between those curves? Neither can the computer. So we don't let a computer choose an exponent. What a computer is very, very good at is choosing a slope. So we can rearrange our equation so that our computer is choosing a slope. And that then looks like this. We take the natural log of both sides, and by doing that algebra, we can take our exponents and turn them into coefficients. And then Logger Pro is very good at finding a coefficient. Now, there is a danger here. There's a trap. Notice that to do this, we need to know what A, B, and C are. Well, actually, we don't need A, which is good because A is the hard one. But we need to know what B is, and we need to know what C is. But if we get B and C from the first equation, then the exponent is going to be whatever we use to find out B and C. Like, that just puts us in a mathematical loop. So it's very important that when you do this log-log thing, B and C have to be empirical values. They have to be things that you measured or someone measured in the lab. Now, it's okay if these aren't perfect, because we know that that exponent, that n, is going to be an integer, because really, are you going to be the person who accidentally discovered the first r to the 1/3 phenomenon? No. No. At most, maybe a half if it's crazy, but really it's going to be an integer value. So you just need B and C to be pretty good to tell if n should be 2 or 3. As long as you're close to 2 or close to 3, you're going to know what the deal is there. So, with those things in mind, what is uncertainty? What is error? How to combine variables? How to do fitting? You have an assignment that you need to complete this week. That is going to be effectively those 3 things. Thinking about error and uncertainty, combining some variables, and fitting some data. Now, the first one is complex enough that I'm going to take the end of this video to walk you through it so you know what you're getting into. But then you're going to do it on your own. It's a little bit of a tricky setup at first if you're not reading carefully. So, your first homework problem looks like this. We have this experimental setup. You are rolling a pipe down a ramp and figuring out the angle of the ramp from the pipe's acceleration, knowing what the moment of inertia is for a hollow cylinder. You are going to calculate the acceleration by several different people using a stopwatch to time when the pipe crosses the 0.5, 1, 2, and 4 meter mark on the track. The question is, where are all the sources of error and uncertainty in this experiment? And how are they going to affect the outcome? Allow me to kind of break down what that hypothetical is. This is a badly designed experiment. It is, I know it is, that's the point. There are many places where this could be done a lot better. That's not the point. The point is you're trying to find all of the little sketchy bits. Is this going to cause error in the system? Is this going to be an uncertainty in the system? Is this going to be an error that is systematic, an error that is random, that kind of stuff. All of these kinds of things, which is a nice like thought process game of like, is this systematic or is this random? But what we actually care about here is, how is that going to affect the outcome? So a good way to think about this is, once you've identified an error or an uncertainty point, is that going to make it appear that the ramp is actually higher than it is in real life? Is that error or uncertainty going to make the ramp appear to be lower than it really is? Or is it going to just make the answer fuzzier and you're going to be able to trust it less? So you need to find all of the sources of error and uncertainty you can find in this admittedly janky experiment, and then classify each of them by, is it going to make the angle appear bigger? Is it going to make the angle appear smaller? Or is it going to make the angle less confident? And is it going to be a small problem, a medium-sized problem, or a real big problem? So that is week 1 of the case study labs. You're going to work through this assignment and then turn it in. And then next week, you're going to get another one of these fun videos introducing you to the intensity at a distance experiments and all the fun that that's going to be. So if you have any questions, feel free to email me, that kind of stuff. I'm around, I'm on Canvas. And I think this is going to be a lot of fun and a very educational thing. I know it seems a little weird and like, where is this lab coming from? I think you're going to like it. I think it's going to be a lot more fun than if I just made you do circuit problems. So, see you next week. Now, these labs, now these labs, too formal. Cha, shapa, shapa, chapa, chapa. No. No, stop talking to you. Talk to you. Let me pull up the schedule. Right? But figuring out, no, that's not helpful. I'm just going to stop there.